Welcome back, calculus students. This is part 2 of the video notes for linear approximations and differentials. In this portion, we're going to be talking about differentials and tying them into the linear approximation we learned in the last video. So you've got your notation dy dx, which we're pretty familiar with at this point. It represents the derivative of y with respect to x, and we're going to just take new meaning to these values. If y equals f of x is a differentiable function, and dx is an independent variable representing a very small change in x, then we can write dy equals f prime x dx, since we're very familiar with dy dx being the same notation of f prime of x. So this is just a rewrite by multiplying the dx to the other side. By doing that, dy, the change in y, is dependent on the change in x. And so dx and dy, these small changes, are called differentials. For each of the following, find dy and evaluate when x equals 3 for a dx of 0.01. So we've got a few more inputs here that the value is dependent on. So let's take our derivative. Dy dx is 2x plus 2. Isolate the dy. That's really the only new thing here. And then we're going to plug in x equals 3 and dx equals 1. So we've got 2 times 3 plus 2 times 0.1, which means that dy is equal to 0.8. And so what this means is if you're looking at the exact moment when x equals 3 and you change it by a value of 0.1, your output or your y value will change by about 0.8. Repeat that process on the second example. Dy dx, the derivative of cosine is negative sine. So dy is equal to negative sine x dx. And then if we plug in our values, it's equal to negative sine of 3 times 0.1. And so our answer for this one, we can just leave exact negative 0.1 sine 3. And that's how we're going to solve for dy. If we put this together with our linear approximation, we have delta y equals, so remember f is your output y, and so this is a plus dx, this is your ending position, and this is f of a, which we're familiar with, which is your starting position, and dx just represents that jump from a to b, and so we're writing this all in terms of a. And just remember that dx has to be small. Rather than calculating the exact change in y, we can use a linear approximation to get close enough. So if we're solving this, remember the linear approximation, we introduce a new notation, but we're basically saying that the actual function value is approximately equal to the linear approximation, and then we can start simplifying. So we're going to say f of a plus dx is approximately LA plus dx equals f of a plus f prime of a. And then if you see here, these a's are going to cancel, and we just left with dx. And then we're going to do some sneaky algebra here with some manipulation. And we're going to subtract this f of a to the other side. And so what that leaves us with is f of a plus dx minus f of a, which is what we have up here. So we can basically say that delta y is approximately equal to the linear approximation, which is f prime a dx. And so we're going to conclude that delta y is equal to f prime a dx. And this is going to be our formula for differentials. And up here, this was just the explanation of where that formula comes from. So let's compute delta y and dy at x equals 3 if dx is equal to 0.1. So for this example, we're going to let y equal x squared plus 2x. And this example was actually done earlier as well. So we're just going to try it again using this new approach. First, compute delta y. Delta y is the actual change in x. So delta y is going to equal f of 3.01 minus f of 3, which in our case is going to be 3.1 squared plus 2 times 3.1 minus 3 squared plus 2 times 3. So typing this into our calculator, we've got 3.1 squared plus 2 times 3.1. So we've got 15.81 minus 9 plus 6, which is 15. So we find that our actual delta y, our actual change in y, is 0.81. If we use the differentials and linear approximation approach, we know that dy is equal to f prime of a dx. And so we're going to take the derivative of this function and plug in x, and then times it by dx. And so that's 8 times 0.1, which is 0.8. And you can see that these are within 1/100th of each other. So this is a very close approximation of the change in y. Now, the last thing we need to talk about for these video notes is error, because if you're doing an approximation, then you're inviting a certain amount of error. So for example, I have 1/100th of error between these two approximations here. If we are indeed approximating, we are inviting a certain amount of error. Propagated error is the difference between the exact value of the quantity and its measured value. The dx is referred to as the measurement error, and the propagated error can be given by the formula delta y equals. So your propagated error is your change in y. So our estimated propagated error uses the same estimation formula from before. Let's take a look at an example. Suppose the side length of a cube is measured to be 5 centimeters with an accuracy of 0.1 centimeters. Use differentials to estimate the error in the computed volume of the cube. Well, volume of a cube is x cubed. So if we are approximating the error, we're going to take that derivative, plug in our given side, and then your accuracy in your measurement is your dx, just so you know, because that's the amount of measurement error you're inviting. So times 0.01. That gives us 75 times 0.01, which is 0.75 from our calculator, which is awfully low. So wait, hold on. Our dx is 0.1, and I wrote 0.01 instead. So let's fix that. 0.1, that makes the error 7.5. So then the next thing we want to do is compare this estimated error with the actual error. So if the measurement varies by 0.1 in either direction, that means the sides are 4.9 or 5.1. Well, what's 4.9 cubed and what's 5.1 cubed? So we've got 4.9 cubed, which is 117.649. And we've got 5.1 cubed, which is 132.651. And if you think about it, our volume of 5 centimeters is supposed to be the middle value, which is 125. So our estimated error, our potential error, this is our estimated error here. And if we compare that, we're going to do 125 minus 117. Figure out that amount of error on the low end. Gives us 7.351. And then on the high end, that's our dV, we've got 132.651 minus 125. 132.651 minus 125, which is 7.651. So our estimated error was about 7.5 cubic centimeters. And if you compare that to the actual error, it goes from 7.35 to 7.651, which is about 0.15 cubic centimeters off. Compare the estimated with the actual. So very close. Within 2/100ths of a cubic centimeter. No, within 2/10. I'm having an issue with my decimals today. Okay, delta x and delta y are referred to as absolute errors because they are the exact amount of error. But generally, a lot of times, you don't care about the amount of error, you care about the amount of error relative to the size. So if you're talking about a cube the size of a house, 0.2 centimeters is nothing. But if you're talking about a microchip, 0.2 centimeters is massive. So we need to think about our error as relative, which is just a ratio describing the error divided by the quantity. If you leave your answer as a decimal, you're going to call it relative error. And if you leave it as a percent, you just call it percentage error instead. So let's take a look at the measure of the Earth. An astronaut is using a camera to measure the radius of the Earth as 4,000 miles with an error of plus or minus 80 miles. Use differentials to estimate the relative and percentage error using this radius to calculate the volume of the Earth, assuming that the planet is a perfect sphere. So our volume formula for a sphere is 4/3 pi r cubed, and the derivative of this is 4 pi r squared dr. So then, if we've got our estimated error, so this is our dr, and we've got our radius at 4,000, we know that our error is approximately 4 pi 4,000 squared dr, which is plus or minus 80. So that tells us that our relative error is this measured error with the derivative. Oops, that's pretty far away. Let's fix that. We're going to do negative 80 on the low end. And then same thing, but with positive 80 on the high end. 4,000 squared. And then we want to divide that by the original quantity, which is our original volume. So your denominator here and here needs to be the volume for that given radius. So that is going to be 4/3 pi, r is 4,000 cubed. And then we want to leave our answer both as a decimal, pi 4,000 cubed, and as a percentage. So go ahead and practice or try typing this into your calculator, and let's see what decimal we get. And I'm just going to do it on the negative 80 side because I know I'm going to get the same answer on both sides. One answer will be positive and one answer will be negative, but they are essentially the same. So I am getting negative 0.06, which means my relative error is 0.06, or my percentage error is 6%. And this concludes the video notes for linear approximations and differentials. Thank you for watching.